we have discussed the linear operators, and we have seen the property also, one result, that if t be a linear operator from dt to y, where x and y are norm spaces over the same field, then t is continuous if and only if t is bounded. So, this is a very interesting result, that in case of the linear operator, the continuity and the boundedness are the same thing. So, you have to only prove one side, either t is continuous, then automatically it comes out to be bounded, or if t is bounded, then it will be a linear operator, then this will be a continuous operator provided t is linear. So, as a corollary of this result, we can further derive this result, let t be a bounded linear operator, then x n converges to x in the metric of, in the norm of x, where x n and x belongs to the domain of t, then it will imply that t of x n will go to t of x. And second result, which can be derived from here, the null space that is N t is closed. The first result follows immediately, because t is linear, bounded linear operator. So, it will be a continuous, and because of the continuity, it will transform the convergence sequence to a convergence sequence. Otherwise, also one can prove it in other way. Say t is given to be a bounded linear operator. So, we can say t of x n minus t x, this is equal to norm t of x n minus x, because t is linear. Then further t is bounded. So, we can say this is norm of t into norm of x n minus x. Now, it is given that x n converges to x in the norm of x. So, this part will go to 0 as n tends to infinity. Therefore, this will go to 0, hence the result follows. So, nothing to be. Similarly, conversely, similarly we can prove the second part also. The null space N t is closed. What we have required is that all the limits points of this any sequence which is in N t must be the point in N t. So, let us take any arbitrary element x belongs to the closure of the null space. Now, if I prove that this x belongs to N t, then N t will be closed. Okay. So, since it belongs to the closure of N t, closure of N t means either it will be a point of N t or maybe the limit point of N t. So, if it is point of N t, nothing to prove. So, if it is a limit point of N t, then there exists a sequence x n in N t such that x n goes to x. Is it not? X n goes to x and that. Now, if x n belongs to N t, since x n is an element of N t, therefore, t of x n will be 0 for all n, because null space means set of those points where the images are zeros. And since x n converges to x and t is x n converges to x and t is bounded linear operator. So, by the part first, t of x n will go to t x. So, we can say from here that t of x n will tends to t of x by first, but t of x n is always with 0 because this is in n t, therefore, it will implies that t of x must be 0. So, this shows x must be a point of n t. So, n t will be closed. Clear? So, as a corollary we can derive these two results, that the boundary linear operator transform the convergence sequence to the convergence sequence, and the null space of that boundary linear operator will be a closed set. Okay. We can further go deeper to the properties of this boundary linear operator. The properties that just like a functions, if f and g are the two functions, one can introduce the concept of composite functions f and g, provided the domain and range suitably satisfy the condition. So, let us suppose T 1 is an operator from by to z, T 2 is an operator from x to y, and both are say bounded linear operators, bounded linear operators, where x, y, z are norm spaces, Okay. And let us suppose T be an operator from x to x is also be a bounded linear operator. So, here it is our x, this is y, this one is z. We assume suitably the norm on these. X to y, the operator is defined as T 2, from y to z the operator is defined as T 1. So, if we take any point x, we want to send directly to z, then we get a composition operator as T 1 compose T 2 is an operator which can send transfer x to z, that is T 1 composition T 2 x, that can be written as T 1 T 2 x. Now, T 2 is a mapping from x to y. So, the T 2 x will be point of y, and if the domain of T 2 range of T 2 x lies in the domain of T 1, then this is well defined, and we can say this will be a point in z, because T 1 image of this will be, if the domain of say T 1 covers the range of T 2. Okay. So, we can say like this. Now, once we have T 1 and T 2 both are bounded linear operator, then it can be shown that T 1 composition T 2 will be a bounded linear operator, from x to z, and not only this, the norm of T 1 T 2 can be shown as less than equal to norm of T 1 into norm of T 2. The T 1 T 2 is linear operator can easily be proved, because if we replace x by a combination alpha x plus beta y, the correspondingly the change will come over here, that is alpha x plus beta y, or we can say T 1 T 2 linear. So, what we do is, let us start with T 1 composition T 2 alpha x plus beta say x 1, where x and x 1 are the point of capital X. Then according to this T 1 T 2 alpha x plus beta x 1, but T 2 is linear from x to y. So, it will convert into the, by property of the linearity, we can get from here is T 1 alpha times of T 2 x plus beta times T2 x 1. Again T1 is linear, again T1 is linear. So, we can further write alpha T1 T2 x plus beta T1 T2 x 1, and that shows the T1 T2 is linear operator. And boundedness also it can be proved. The norm of T1 T2 is basically the supremum of norm T1 T2 x and divided by norm x, because the norm of T1 T2, this is the supremum of norm of T1 T2 x divided by norm of x, and then x belongs to the domain of T1 T2 like this. Okay. So, similarly, we can show like this, and finally, it can come out to be the less than equal to norm of T1 into norm of T2, is because this is again T1 is bounded. So, we can write this is less than equal to norm of T1 into norm of T1 into supremum of this thing, that is norm of T2. Clear? So, we get from here this is okay. Now, as a particular case, if T is an operator from x to x, say be a bounded linear operator on the norm space x, norm space x, then we can say that norm of T to the power n, this is less than equal to norm of T to the power n, where the n is a positive integer. Just by induction this we can show, by induction we can prove this thing T1 T2. So, let T1 is equal to 2, T2 equal to T, and we get this result. Continue this for n equal to k, then k plus 1, one can show this result holds. So, this is also one of them. Now, there are another concepts, just like in mapping we have a similar concept here, the equal operators. We define the two operator T1 and T2 operators T1 and T2 are said to be equal or said to be equal if their domains are the same. If domain of T1 is the same as the domain of T2 and the corresponding range set is also there, that T1 x equal to T2 x for all x belonging to the domain of T1, which is the same as domain of T2. So, just like a mapping, two functions are said to be equal if the corresponding domains are same and the range set are equal. They take the same values for each x, for x belonging to the common domains. Okay. So, here also we equality has a now a new concept which we introduced one to a restriction and extension of an operator of the operator. Okay. What is the restriction of the restriction of an operator T from domain dt to y to a subset V of dt is defined, is denoted by T restricted on B and is the operator defined by the restricted operator T on B is a mapping from B to Y such that the images of any element x under T B will be the same as the image of x under T for all x belonging to B. The meaning of this is, say suppose this is our dt and here it is V, which is a subset of dt. T is a mapping from dt to certain range set, say by all the elements of B need not be the elements of dt, because B is a subset of dt. We are interested to define an operator on B such that the image of this operator, the image of any element of B under this operator will give the same values or gives the same value as the T of x. Then we say T restricted B is the restriction of T on B. That is, we are reducing the domain of T B to a subclass, or we wanted to redefine the operator T on a subclass in such a way that images are same. Clear? So, such an operator T B be called a restricted operator or the restriction of the operator T. The reverse of this process we call the extension. That is, we say extension, an extension T delta, say of T is an operator from M, which is a superset of dt, to say by, such that when we restrict this T delta on dt, then it should amount the T, that is the image of any element under T delta, that is the image of T delta x should be the same as T x for x belongs to dt. So, just like here we are reducing the domain for T delta. T delta is defined over the bigger class, where T is defined on the smaller class. So, T delta is called the extension of T. So, we wanted to extend it. This is our say M. So, here when we are defining, then this definition will give the T delta. Now, when T is given to be a bounded linear operator on a domain D and we wanted to extend its domain of definition. So, it means we have to define some operator T delta, which will be an extension of the operator T. Now, when you define or when you extend the operator T to T delta on a bigger class M, then we may or may not be able to retain the properties of the operator T. For example, the T, if it is a linear operator, the T delta may not be linear. If T is bounded, T delta may not be a bounded linear. So, there are infinitely many ways of extending the definition of T for over a bigger class. But what we are interested in, we wanted to give an extension of T to T delta over a bigger class M under the restriction that a minimum property that is linear property, boundedness property are retained. So, that extension will be useful, because we are extending the domain, we are enhancing the domain. Instead of dt, we are considering the bigger domain, and the operator which so defined is not losing the property of boundedness and linearity. So, this will be a useful extension, and under what condition this useful extension is possible, that we will see in the next result. So, the next result tells how one can retain the boundedness and linear properties of an bounded linear operator when it is extended to a bigger class. So, this result is given in the form of theorem. What theorem says? Let T be a operator from dt to y and be a bounded linear operator, where dt lies in the norm space and y is also a norm space. In particular, complete norm space. Y is a complete norm space, that is, Y is a Banach space. So, suppose T is a bounded linear operator from dt to y, where dt lies in the norm space and y is a Banach space. Okay. Then T has an extension T delta defined from dt closure, this is the closure of dt to y, where T delta is a bounded linear operator of norm same as the norm of T. So, this result says that if we extend the domain of dt to its closure and replace by the range set to be a subset of a Banach space, that is, y is a Banach space, then this extended operator T delta will remain bounded linear and the norm will be the same as the norm of T. Okay. So, this theorem says how one can extend the bounded linear operator to a bigger class under the restriction that the boundedness, linear property and the norms are retained. Okay. Let us see the proof. So, in order to prove this, first we will show the existence of T delta, because T is given, is a bounded linear operator is given. So, we have to first justify that such a T delta will exist, and second one, if it exists, then it should be bounded and linear, second part, and finally, we will show that both are having the same norm. So, to show the existence of T delta, we should see that T delta is defined over the entire class X T dt closure. So, let us take a point x in the dt closure, which is an arbitrary point in the dt closure. Now, since it is a closure point, x belongs to the closure of dt. So, by definition, there exists a sequence x n in dt such that x n converges to x. Clear? Because x is the limit point. So, there must be a sequence of the points in x n available which converges to x. Now, since T is linear as well as bounded both, so we have norm of T x n minus T of x, this is equal to norm of T x n minus x by linear property, and then because of the boundedness we can say this is less than equal to, no, this is because of the boundedness of this. Now, since x n converges to x, so this norm of x n minus x will go to 0. Therefore, this x n, let us take m here, okay, T of x n x m x n x n. Since x n converges to x, it is a convergence sequence. So, it is must be a Cauchy sequence. So, this Cauchy sequence, this will tends to 0 when n m goes to infinity. So, as n m tends to infinity, this implies that sequence T of x n is a Cauchy sequence in Y, but Y is complete, because this x n converges to x is a convergence sequence, every convergence sequence is Cauchy sequence. So, this will go to 0 when n m tends to, therefore, this will go to 0 when n m goes to infinity. So, T of x n behaves as a Cauchy sequence in Y, but Y is given to be Banach. So, every Cauchy sequence must be convergent. So, since Y is Banach space, so this Cauchy sequence converges. So, the sequence T of x n converges in Y. Therefore, there will be a point in Y belongs to capital Y such that T of x n will go to Y in capital Y. Okay. So, now what we get? This is our x, this one is Y. Here we are getting the sequence x 1, x 2, x n, which goes to say x. The corresponding sequence T x 1, T x 2, T x n, this converges to Y. Okay. So, this x may be the point, this is the dt, I am taking this is, okay, say this one is dt, let me just point out, say this is our dt. So, this point x may be a point on the boundary, maybe the point on the boundary. So, this is the point x, here we have x which belongs to the closure of dt, Okay. So, we are able to define an operator T delta such that the image of this T x becomes Y. So, we define T delta by T delta x is equal to Y. So, existence of T delta is guaranteed, that we can get that image of x belongs to T delta to Y, an element of this. Now, this definition of T delta should be independent of the choice of the sequence which converges to x. Suppose there is another sequence which goes to, this is our dt closure and here it say x. Now, this is a one sequence, this is another sequence. Suppose I take a sequence which is combined to this and it converges to x, then since it has a subsequence which converges to x, this has converged. So, this sequence will also converge to x. So, this x limit, the definition of T delta which you define is independent of the choice of the sequence which goes to x. So, nothing. Now, clearly T delta is linear. Why? Because the T delta x is defined as basically the limit of this T x n. Basically, what we are doing, the limit of T x n as n tends to infinity, this is defined as the T delta x, is it not? Because this is equal to y and y is equal to T delta x. So, T is linear. So, if we take the T of alpha x n plus beta say x n dash, then because T is linear, we get alpha T x n plus beta T of x n dash, and then taking the limit as n tends to infinity, we get from here is T delta alpha x plus beta x dash becomes alpha of T delta x beta of T delta x. I hope this will be clear, because it is a direct proof, nothing to it, it is very simple. To show the T star is linear, take the help of its definition. The T star x is equal to y and y is obtained as limit of the T x n. So, we can say the limit of T x n which is equal to say y is equal to T star x. So, taking the help of this T as a boundary linear operator, we can show immediately that T delta is a linear operator. Similarly, one can show that T is also a bounded operator. That is okay. Let us see how. T is linear, clear. Now, T star is an extension of T. T star is an extension of C, because for every x belongs to T, because T delta x coincide with T x when x belongs to d t. For every x belongs to d t, it means that T delta and T are equal on the subset d t. T delta is defined on closure of d t. So, it is an extension of T. Now, to show T star is bounded, what we do is we start with the norm of T x n. Now, this is less than equal to norm T into norm x n, because T is bounded. Okay. Now, as n tends to infinity, as I told earlier that this T of x n, when you take the limit as n tends to infinity, is by, which is equal to T delta x, by which is the T delta x, and this x n, limit of this x n when n tends to is x, but norm is a continuous function. So, limit of the norm x n as n tends to infinity is norm of x. So, from here if we take this as n, we are getting this is norm T delta x is less than equal to norm of T into norm of x. So, there exists a constant C such that norm T delta x is less than equal to C times norm x, therefore, T delta is bounded. Okay. Then to show the T delta norm is the same as norm of T. Okay. This to show, from here we get norm of T delta x divided by norm x is less than equal to norm T. This is true for every x belongs to the domain of d t closure. Hence, take the supremum. So, supremum of 4 x belongs to d t delta and x is not equal to 0, is further less than. So, this shows the norm of T delta is less than equal to norm T. Clear? The converse is automatically true. Conversely, norm of T delta will always be greater than equal to norm T, as the domain of T delta is bigger than the domain of T. So, when you extend it, the definitions are extending, the length will be enhanced, not it will not be reduced. So, we always get this is greater than equal to this. So, combine these two, we get norm of T delta and norm of T is the same, and that proves the results. Okay. So, this result says that we are able to get an extension of a boundary linear operator to over a class which is the closure of the earlier class d t, and the properties of the boundedness and close and linearity are retained. Okay. That's now, so far we have considered the bounded linear operator, in which the domain and range both were the normed spaces, also a vector space when you take the linear operators. Now, when the range of this set operator is replaced by the field of a scalar, that is either a real number or a complex number, or a field in general a scalar field k of the norm space x, then such a operator we call it as a functional. So, a bounded linear functional is basically a bounded linear operator. Is a bounded linear operator where the range lies in the boundary linear operator with domain in a vector space in a norm space X and range in the vector space or norm space, you can say, K or vector space or range space of scalars field K. Of X. That is the meaning of this is, say X be a vector space suppose, then there are two operation addition multiplication, and if it is a norm space then we say this is a norm space. But when you take X to be a vector space, basically we are not writing K. This is a field of scalars on which the vectors are defined. So, X is a norm space or X is a vector space over the field K. This K may be a R or it may be a C. If it is R, we say the real vector space or a complex vector space. So, what we see here, that when an operator T from X to K, K is either R or C, then this T be denoted by F and is called a linear functional. If X is a vector space, okay, provided it satisfy the condition of the linearity, provided it is a linear condition of linearity are satisfied. Okay. But if X is a norm space, then we call it this as a bounded linear functional. Okay. So, we define the bounded linear functional as a bounded linear operator, where the domains remain same in the norm space X, but the range in place of the y we are taking a in the field of scalars K of X. So, if X is a real vector space, real norm space, the field K comes out to be R. If X is a complex norm space, K comes out to be the C. Okay. So, we define the bounded linear. Now, once it is the bounded linear, the norm is defined like this. So, we say a bounded linear functional F is a bounded linear operator with the scalars field of norm X as a range set. Okay. So, boundedness we say, let F is a mapping from X to R or C is a bounded linear operate functional if F is linear functional and there exists a C greater than 0 such that mod of f x is less than equal to C times norm of x. So, that will be equal to. So, if there exists a number C such that for all x, that is for all x, this is true. This is true for all x belongs to the domain of f. Again, the minimum value of C is called the norm of f. So, the norm of f is the supremum of mod f x over norm x, where the x belongs to the domain of f, x is not equal to 0. This is called the norm. So, just like a previous case, we can define the norm of the boundary linear function as this. Hence, the relation we can say the mod of f x is less than equal to norm f, norm x holds for every x belongs to the domain of F. Okay. So, this result must be true. The same results which we have proved earlier in case of the boundary linear operator continue to hold good in case of the boundary linear functional. For example, if F is a bounded, F is a linear functional, then continuity and the boundedness will remain the same, and one can find out the corresponding results which we have proved in case of the boundary linear operator holds good for the boundary linear functional. Now, there are certain examples of boundary linear functional. Okay. Let us see the norm. The norm is a mapping basically from a vector space X to R, if it such that image of X takes the value norm of X. It is a non-negative real functional, real valued function, and satisfy those conditions norm X is greater than equal to 0, norm of alpha x mod alpha into norm X plus y is less than equal to norm X plus norm y, and so on so forth. Okay. Now, this norm we claim it is a bound, this is a functional, is a functional, because this is a real valued thing, this is the real valued number. So, it is a scalar quantity. So, mapping from norm space to a field of scalars R. So, it is a functional, but it is not a linear functional. Why? Why is not a linear functional? Because if we look this simple property x plus y norm, it is not equal to the norm of x plus norm of y, rather than it is less than equal to. It means the linear properties are not retained. So, that is why norm is not a linear functional, it is a non-linear functional, okay. But it has a lot of importance. Another example is our dot product. This we have already seen, if dot product is a functional. In fact, a mapping F from R 3 to R, if we define H f of x equal to or x bar equal to x bar dot a bar, where a bar is a fixed vector in R 3, this is a fixed vector, while x bar is a variable one, but the dot products comes out to be a scalar quantity. So, this is a functional, it is a linear functional. So, it is a linear functional. In fact, we will show it is a bounded linear functional. Linearity follows immediately, replace x by alpha x bar plus beta x 1 bar, we can see, and the boundedness is shown like this, mod of this equal to mod of x bar dot a bar, which is less than equal to norm of x into norm of a, and then divide by norm. So, we get norm of f is less than equal to norm a, okay. And conversely, norm of f, because it is the supremum of mod f x over norm x over all x belongs to the domain of f, x is not equal to 0. So, we can say this is greater than equal to a particular value, say a bar, this is a bar, okay, a bar divided by mod of a bar. And when you say apply this condition, this is equal to mod of a bar dot a bar divided by norm a bar. So, it is equal to basically norm a bar, because this is norm a bar square, and we get. So, from here we get that norm of f equal to norm a bar, that is this dot product comes out to be a bounded linear operator with the norm equal to the norm of the fixed vector a bar which we have chosen. Another generalized result example is our definite integral. Though when we say the definite integral a to b x t dt, when x is a fixed continuous function, then this gives a number simply. But when we say x is a variable one belonging to the say set of all continuous function defined over the interval a b, then we denote this by f x and it becomes a functional defined on x. Now, this functional is a linear functional. So, it is a bounded linear functional, and in fact, we can show that norm of f equal to b minus a. I think this one way it is clear, because norm of f, if I look, this is the supremum of mod f x over norm x. So, replace x by a, where such that norm of x equal to norm of a 1, norm of x is equal to 1, replace x by such x naught, where this is 1. So, if we replace with this by now, then we will see it is greater than equal to b minus a. Okay? And conversely, mod of f x we can write it, mod of f x is less than equal to integral a to b mod of x t dt, which is less than equal to maximum value of this x t, but this is the maximum is norm. So, basically this is b minus a into norm x, divide by this. So, we get mod f x over norm x, take the supremum is less than equal to b. Okay. So, combine these two, we get norm f equal to b minus a. So, definite integrals, they are also behaves as a bounded linear functional having the norm equal to the length of the interval on which it is defined. Then we can also think the example of L2 space. If we take L2 space, this is a Banach space, norm space, and if we fix that one element and define f x as sigma x I into alpha I is 1 to infinity, where alpha is alpha 1, alpha 2, alpha and so on is a fixed sequence, and x which is x 1, x 2, x n is a variable one, then you can see that this will be a bounded linear functional defined on L2. I think you can just go. The bounded linearity follows because f is bounded linear functional on L2, because what is the mod f x? Mod f x is mod of sigma x I alpha I is 1 to infinity, which is less than equal to sigma I is 1 to infinity mod x I mod alpha I. Now, use the Cauchy-Schwarz inequality. So, by Cauchy-Schwarz inequality, this can be written as sigma mod x I square under root into under root sigma mod alpha I square I is 1 to infinity. But this part is nothing but the norm of x, and this is a constant c. So, it can be written as c times norm of x, and this shows that f is a bounded linear functional. So, we have seen the so many examples of the bounded linear functional as well as the bounded linear operator. Now, with the help of this functional, since our x be a norm space and one can introduce that on it the functional linear functional bounded linear functional on x. Now, what will be the corresponding space of the linear functional or bounded linear functional, that we see from here. Suppose x is this vector space, let us take this is a vector space, and we are considering another set f, g, h etcetera, which are f, g, h, these are the linear functional functional defined on X. So, let it be denoted by this say X star. Clear? Now, this linear functional, whether it form a vector space again or not. If it forms a vector space, then it will be a useful structure, and we see that if we define the suitably the mapping on this boundary linear functional. So, let X be a vector space, X be a vector space, okay, and X star be the set of all linear functional defined on X. We claim that X star forms a vector space, under these two operations, under the operations f plus g x as f x plus g x, while alpha f x equal to alpha times f x. That is on X star. If I introduce the addition and scalar multiplication in this fashion, then all the property of the vector space are satisfied, and this will be shown that X star, it is easy to prove. Okay. So, it is easy to verify the conditions. Okay. Conditions. So, this space X star becomes a vector space. This space becomes a vector space. Okay. So, now we are having this space X, and then this also becomes a vector space. Then one can further think the linear function defined on X star. So, we can further write another space say X double star, say mapping is psi, eta, etc., which are the functionals on X star, and if it is again a vector space, then the question arises what will be the relation between X there. Okay. So, we can further define linear functionals on the vector space X star and denote this vector space so obtained by X double star. Clear? And in a similar way you can introduce the concept of addition multiplication. Now, my question is, we have started with a vector space X, this is a vector space, then we have got another vector space which is a linear functional, then another vector space X double star. My question is, what is the relation between these two? Can we connect X and X double star? If we are able to connect such a by a mapping, then this will be a useful mapping, and one can identify these two spaces, so many properties in these two. So, this we will discuss next time. Thank you.